Okay, hi everybody. Today we have the pleasure of having Professor Houman Homayoun visit us and giving a talk. Professor Homayoun is at UC Davis, recently moved there from George Mason University, and then having a PhD from Irvine, UC Irvine, and master degree from Victoria in Canada, and an undergrad from Reef University in Tehran. Professor Homayoun is working with cybersecurity and heterogeneous computing and other interesting architectural topics. He's published over 100 papers in good venues, very good venues, have a best paper award in GLV, LSI, and so on. And we'll be talking about cybersecurity, which is really hot, so please.
Thank you so much, Genesis, for the kind introduction and also hosting this last-minute talk. Thank you everyone for attending the talk. My today's talk is on hardware cybersecurity. I intentionally call it cybersecurity, not really security, because as I'm going to show you, this field of hardware is not just about securing the hardware, but also bringing a lot of concept from cyber community, addressing a lot of problems that cybersecurity community has been dealing for the past maybe 20, 30 years, like malware, Trojan, antivirus. But now, as a maybe computer engineering community as a whole, or hardware security community, a smaller part of it, we have solution, new solution, alternative solution to address some of this challenging problem, and we'll see how this problem looks like. So let me first quickly introduce the lab that we are working. It's called Accelerated Secure and Energy Efficient Computing. We do some fundamental computer engineering related topic, and the application could be in security, the application could be for energy efficient computing, a lot of similar topic, a similar concept, different topic. We have group working on auto-tuning, big data framework, machine learning acceleration, hardware security, reverse engineering, and also architecture and system security. And also recently, not so much recently actually, about a year and a half ago, we are working on adversarial machine learning and obfuscation. So just a quick overview of some of this research. Two main topics, energy efficient computing and hardware cybersecurity. One of the first projects that got funded from NSF, National Science Foundation in US, we actually promised to develop a biomechatronic interface for prosthetic arm. So essentially, the idea is we have ultrasound band, we put it around someone who lost a limb, for instance in this case arm, and then we collect image in real time. These are the images you see on the right. We collect these images in real time. They're very noisy, and then we try to understand motion. Like if someone lost limb, go extension, flexion. From these images, we try to understand different gesture of the hand. But it appears that simple maybe gesture are easy to detect, but the more complex one, like rotation and flexion, something like this, are very difficult. But this project started in 2013. We delivered it in 2018. Also, my colleague started the company out of it, and I think I have a video. So my responsibility and my team responsibility mostly was to design an accelerator for all these image processing applications. They're very intensive. We receive image in perhaps 10,000 every second. And if we started with, at that time, 2014-15, we started with NVIDIA Tegra, first generation, didn't work out. Tegra 2 didn't work out. Eventually, we moved to FPGA, to Accelerator, to make it customized, because the front end, we receive a lot of image, we need to buffer them. Tegra doesn't have that capability. So FPGA tends to be more powerful, dealing with a lot of image in short amount of time when you receive image streaming. So I think I have a video. Let me see if I can play it here. So this is actually how it works. We connected the software on the computer, try to emulate what, and for some simple operation like pinching. But one challenging part of it is for someone who lost limb, first you have to work with them. So to remember, when they want to do extension or flexion, how it looked like when they had maybe that limb in place. So my colleague spent about a year working with several patients to essentially train them or retrain them, remind them that these muscles, they had memory at the time, still they have memory, but to essentially train this memory to some of the basic operation that they used to do, but now they cannot do it, especially after 5-6 years. This patient had an accident, they don't remember exactly what these operations were doing and how muscle activity would look like to do it. But it turns out that once you train it, they can quickly pick up and follow a lot of basic operation that they can do. Okay, so another project that we were doing was developing heterogeneous accelerator for data-intensive computing. We started this project in 2014, published several papers, FCCM, CC Grids, Codes ISS, and so on and so forth. But what essentially we're doing different from the beginning from several other groups was we started by using 2014 Zinc platform, which was relatively new at the time, stack them and try to build an accelerator cluster out of this Zinc. And here I show it 3 node that we designed in 2015. We stacked them and with almost each of them $70, 3 times $70, $210. We can get 2x to 3x performance improvement end to end. Back then for Hadoop MapReduce, for Spark also we tried it, but this is really substantial. 2x to 3x is substantial by itself, but you could argue that, okay, with many node server we can get that performance. But this is like essentially to put in perspective of how much valuable this number is, we compare it with a 6 node server. 6 node server, Xeon server, 6 times 5,000 roughly, or maybe 3,000 roughly, depending on the technology, would be 20,000. We are matching it with 1 node server plus $210 accelerator. So when you present this number to maybe investor, they're happy, they like the number. Then they understand how valuable that 2 to 3x is. So also on accelerating embedded system application, we look at several biomedical applications. We develop many core platform, we call it PENC, power efficient nanocluster many core. And we deploy several applications, multi-channel seizure detection, physiological stress detection, and standalone tone drive system. And the number also pretty good. This is also one of the early research that we were doing, starting in 2015-16. So on the big data, we have a project on autopilot computing or auto-tuning, mapping, and co-scheduling data-intensive application for energy efficiency. When it comes to mapping big data application, again, I call it big data, but you can use data intensive, different community use different terminology. The difference from standard application is these applications, they have many tuning parameters. For instance, for Hadoop MapReduce, we have about maybe 10, 20. For Spark, just on the software side, we have 30 tuning parameters. 30 tuning parameters, each taking 4 or 5 different permutation. The total number of possibilities, you have to try to find the most energy efficient one. The space is enormous. You cannot really explore the space in linear time. So on top of that, add tuning parameter at the hardware level, such as voltage and frequency. And add more tuning parameter at the application level, the size of the data that goes to each node. So here I listed several. HDFS block size for MapReduce at the software layer, maybe between software hardware layer, core microarchitecture if you have a heterogeneous architecture, big little number of mapper, number of reducer, size of data per processing node, operating voltage frequency, real-time constraint, application phase, and so many other. So all of these parameters, when you schedule your job to the cloud or to cluster, tuning them effectively would significantly change the energy efficiency of the application. And when I say energy efficiency, essentially in the computer architecture community, we look at EDP, energy delay product, or ED2P, depending on how much emphasis you put on real time. The more time, the more essential emphasis you put on the real time behavior of the application. And developing an auto-tuning feature is important. So the end user that submitted jobs to cloud doesn't care how the cloud manages, it just gets the performance. On the cloud side, however, managing energy is important. If cloud can give you the same performance, but at much lower energy, it's essentially winning because it saves a lot of energy. So on the cloud side, the end user what we believe is that you shouldn't care about how to tune them. The cloud should deploy a software layer that, based on the running application, do some initial profiling, learn what the application is doing based on some small data set. Maybe run your application for weeks with very large data. The cloud run the application with a small sample of data, few megabytes, few gigabytes, understand what the application behavior is, and then using some machine learning algorithm, tune all of its parameters to not the best setting, but close to the best setting, or optimal essentially. And that is very important. Okay, on the hardware cybersecurity side, the very first project that our lab was involved with was work with General Motors back in 2013. GM gave us 2014 multimedia system for the car, and they essentially just told us the contract was very simple: hack the system. No communication with GM. We essentially serve as a white hacker, or we call it ethical hacker for GM. The project has full limitation on publication, essentially restriction, but it was a lot of interesting learning experience for us. So in this case, what I'm showing is from the Bluetooth system, we were able to hack to the multimedia system. I put a logo of George Mason University on the multimedia system. So we found a lot of vulnerability in the system for obvious reasons. They didn't want us to publish because that doesn't make sense for economic reason. But we found many vulnerabilities. Hardware, software, JTAG was enabled. Even GM really doesn't know where inside the box where it comes from. Maybe they get it from LG. LG inside there are about 200 memory. Okay, out of 200 memory, 20 come from Sky Hynix, 20 come from Samsung, 20 comes from no source. Even they don't have name. We found replication of operating system, various parts. It was essentially a mess. But it's not just for GM, it's for almost every company. Most of the companies, they don't have a security mindset when it comes to all of these components. And this is really scary because this is an attack gate to the entire car. Once you're able to hack the multimedia system, from the multimedia system you go to the CAN bus, and from CAN bus you have control of the entire automated system. And this is going to happen more and more. The first group that we were able to hack it and publish it was a group in Australia in 2011. So essentially GM wants us after 2 years to replicate this for their car. And again, it was interesting learning experience for us.
And where the vulnerability lies actually? In the canvas or behind it?
Not in Canvas. Actually, we didn't look at the Canvas vulnerability. We treat this as a standalone module. Canvas would sit after, right? We just want to understand the vulnerability of this standalone multimedia system. Yeah. If we can hack it, then we have access to Canvas.
We have to go through the Canvas in order to access the rest of the system.
Yes.
So if the Canvas is vulnerable, then you have a really big problem.
Yes, I totally
especially
agree.
in cars.
Totally agree. Yes, and Canvas also there is no really notion of security in Canvas. They haven't been in place. And for this particular case, we hack it through Bluetooth communication. So from the Bluetooth, we go to the multimedia, and then once we are in the multimedia system, the Canvas doesn't care who controls the multimedia system, whether the Bluetooth attacker like me or the multimedia system, a CD, a USB, or whatever sits there. Then from there, we can do whatever we want on the Canvas.
So you claim that the Bluetooth server is actually vulnerable, actually?
Not the Bluetooth. So essentially from the Bluetooth, we can connect to this multimedia system, right? But then when
is it easy to bypass the Bluetooth?
No, we didn't bypass the Bluetooth. The Bluetooth is not protected by itself. It's just the Bluetooth we can run music, song. We can even upload document binary. So from the Bluetooth, we upload whatever we want, and then once we are in that space, we can manipulate the system. So on the Bluetooth system, it really doesn't care. As long as it trusts the communication, what we upload, it's not really looking at the packet or whatever it is. So the, yeah, any other questions? Okay. So another project that we recently involved, DARPA had a program called ECE, started about a year and a half ago. That was not really in response to, but they knew about this type of attack before Intel announced it. They started this program, and How many of you have heard of Spectre and Meltdown? So these are essentially known vulnerabilities and also attack on Intel and ARM also architecture. They take advantage of some of the maybe performance feature we put in place, or some inconsistency, cache delay versus memory delay. But essentially they take advantage of surface attack on the architecture. The surface attack, the larger it is, the more advantage they can essentially benefit from. So the goal of the project is to develop first a new architecture that is protected against this type of attack, and second is protect legacy architecture, the architecture that exists today against this type of attack. And for that purpose, we propose several, ideas. We look at, for instance, performance counter, which I'm going to talk about this today, how to detect malware, how to detect vulnerability, and this is going to be the second part of my talk today. So, another program of DARPA that we're working with, DARPA OMG, Obfuscated Manufacturing for GPS. Here we're developing a technique, again, machine learning based, at a circuit level to detect Trojan. And Trojans are really scary. Imagine you have a million gates design, and when you send this design to your manufacturer takes this millions gate, but now today we are talking about billions gate, okay? And insert about 200 gates, somewhere in the critical part of the design, that perform some malicious activity, or they're just sitting idle there and activated at the time that they want to harm your system. How do you detect 150 gates, 200 gates out of billions gates, out of million gates in the design? It is almost impossible, right? Especially given that now we have process variation. Not now, since 2008. So process variation by itself introduces a lot of unpredictability in the design. On top of that, add some more noise, 150. How to detect noise on top of existing noise? It is very difficult, right? So for that purpose, we were working with several colleagues of mine that are in the statistics department, they're statistician, and they're developing method for anomaly detection. And actually, a lot of concept that we're also borrowing it and applying it to anomaly detection as a software layer, as I'm going to show later today. The concept is the same, just the data set is different. And the data set, we need to convert it from X to Y to be able to apply the same technology. The same technology, that actually the technology that I'm going to talk about, a lot of community, like biomedical engineering. Some of the technology that I'm introducing later today, or if there's time, has been in practice in biomedical community for years, since perhaps 1990, 1995. The idea of motive discovery. Motive discovery is when you have EEG, ECG, EMG signal, how do you take anomaly in those time series signal? Everything we do is time series, right? HPC, hardware performance counter data. When we convert a circuit graph to a CNF function, for those of you who have done SMT or SAT solver, this is also, we could think about it as time series data. They were able to detect anomaly in time series human biological signal. Here we are applying the same technology, the same solution to now different data set. So we are not really reinventing the wheel. We're just applying the same idea, but to a different data set. So, okay, so that brings me to the outcome of my talk today. I have two topics. One is on lookup table-based obfuscation, and the second one is on machine learning. But first, let me quickly introduce the field of hardware security, and then we'll see if this is real, and then we introduce the rest of the two topics. Hardware security in the past mostly has been about cryptography. Okay, ancient Egyptian, ancient Greek, ancient empires, essentially, especially during the wartime, they were developing various cryptographic technology for secure communication. Okay, but in today's hardware security field is really different, diversified, and this is mostly related to the complexity nature of today's computer. Today's computer, in fact, are built as a multi-layer foundation. We have on the top layer, we have application, then software layer, then encryption, transport, network, operating system, and hardware. And essentially, we need security at all of these layers. If we don't trust our hardware, no matter how much security we have on the higher level, every effort we are essentially devoting to securing the system would be futile. So the securing the hardware, which is at the core foundation underlying, is very important. To see what software security today look like, let's first take a look at how ICs are designed today. There are many steps involved in designing IC. I'm going to go through this process very quickly. First, the design house, which could be Apple, contact several vendors, Samsung for maybe processor or their own processor, LG/Samsung for LED, for the LCD, whatever they're using, technology for the screen, and they collect all of these IPs and they do the front-end synthesis verification. Once they have the GDS2 or graphical view of the layout, then they send it to Foundry. Foundry could be in Asia, could be anywhere in the world, could be in, now it's globally, foundries are located across the globe everywhere, could be everywhere essentially, and then once it's done, the foundry send it for testing, testing at a wafer level, and next step is packaging and assembly, and finally PCB assembly and system integration. There's so many steps involved to bring IC eventually to the real market. Today ICs are more complex compared to the decade ago. In the past, everything used to be done in one location, okay, or maybe 2, 3, 4 locations. But now, because of the cost, because of globalization, these steps are done in geographically different locations, different countries, and each country are running by different jurisdiction, right? When you're fabricating an IC in Taiwan, you have to follow their jurisdiction. You're fabricating in Abu Dhabi, they have their own. If you're fabricating in France, they have their own. So the fact that the ICs being fabricated, several of this process also for fabrication is done globally, introduce some vulnerability. Okay. Another trend is that the cost of designing, running a foundry is enormous. Essentially, we're talking about $5 to $10 billion to just start running a foundry, not necessarily state of the art. And this is actually what DoD, for instance, in the US is trying to do, to bring up a foundry just one below the state of the art node, working with Intel, working with global foundries, but the cost is enormous. And if the market is not big, it's not going to be really justified. And unless the government is behind it, like government in Taiwan or government in Abu Dhabi, UAE, foundry are going just to keep losing money, like the story that many of you have heard of IBM sold its foundry, and to global foundries even gave them $1 billion to take care of it. So it was all lost for IBM, but they had to do it to supply the customer. Otherwise, customer could sue them in the next 5 years, and it would cost them even more. So because of that, we have now few players on the foundry side that are sitting across the globe everywhere. And if your company is operating in US, in Greece, now you have to trust a company that doing the foundry in Taiwan. How do you trust them? How do you trust them that they don't really insert Trojan in your design? How do you trust them that they don't replicate your design? How do you trust them that when you send your, let's say, ARM licensed Cortex architecture design in this university, that they don't, instead of producing 1 million, they don't produce 2 million. And they sell that 1 million in their own market. In fact, they're doing it. And there are a lot of evidence to prove that they are constantly involved in various types of activity. Because of high cost of globalization, high cost of fabrication, and many other, now you see, most companies in US, most IC major giants, they like AMD, Broadcom, now Avago acquired Broadcom, Marvell, Nvidia, Qualcomm, they're fabless, and they're relying on these third parties. And third parties is not just TSMC, it's TSMC, UMC, Charter, Toshiba, and so on and so forth, and many also in Europe. This is the global foundry map that, again, there are some major players. It used to be maybe 10-15 years ago, a lot of them used to be in US and also Europe. But as you can see, there's a big shift to Southeast Asia. And this is also happening continuously. A lot of foundry, they either they offsource part of them and gradually a big chunk of them. The very last one was the one I told you, IBM Global Foundries moved part of them to Dresden, Germany, the other part of them to Ras Al Khaimah in Abu Dhabi, and business now is running 2 different countries. Actually, there is a very interesting website called SourceForge. You can go there and type in your device information. It tells you your device if it is designed, let's say here, I think that was the data maybe 3-4 years ago, Apple maybe 4, 5, 6, and it's designed in California, but as you can see, the supply chain all over the globe. Even testing could be done in part of Malaysia. But which testing? Testing of the packaging, testing of the assembly, post, pre-layout, post-layout, and so on and so forth. So there are so many steps, and because of that, anything that is done outside of the design house, we call it, or especially out of the design house, out of the country, we call it untrusted source. Because we don't have control over that jurisdiction. It's running by a different one. It's running by different countries. We can't trust it. If they overproduce it, how can we go and test it? And in fact, if you go to TSMC, if you visit TSMC in Taiwan, you will be surprised. They have a town of robots, and they're carrying heavy die wafer, like a human, on their head. And each robots are actually running something around 6 to 7 kilometers inside their fabrication house to fabricate an IC, because fabricating an IC involves various steps, especially depending on how many mask layer you have, and they have to go from one location to another location, and these robots carry these big wafer for 6-7 kilometers all the way around the fabrication house to do various steps. And in those steps, how can you ensure, as a third-party customer, how can you ensure that any of these steps may perform a malicious activity? Or how can you ensure that they don't produce more than what they're supposed to do? It's a complex infrastructure. You don't have control. You just see a representative of them, and that's it. So, because of that, there has been incident of Trojan insertion, overproduction of intellectual property and intellectual property theft, reverse engineering, and counterfeiting. And these are all happening. Where are the sources? The sources essentially could be anywhere. Hardware Trojan could be in location that is shown, overproduction, reverse engineering, counterfeiting, and essentially all of these steps could be vulnerable to any of these malicious activity. So let's see if this is real, or everything I just told you is just to scare you or scare fundraiser, and so they open up their purse and give us some funding, we do research, and we move on. So to best convince you that this is real, I'm using a video from YouTube. It's a public video that they show in 2013-14, one of the DARPA meeting. There's no sound. Okay, let me see. How can I get the sound? Quickly. Oops. Where is the sound? Okay, so you know what, let me do it because the sound is important. This is what I'm going to do. Okay. Yeah, it disables the sound.
You can just comment on what you're saying.
Okay, that's fine. But this is really interesting. So this is a video from CNN, and it showed the inside military equipment, F-18, Poseidon submarine, that they found a lot of bogus electronics, microelectronics. And imagine this is happening for DoD, which they have so much control, so much over the supply chain to validate it. In a real market where security, most companies, they don't make money out of security. Security is a byproduct. They have to make sure that the product is secure enough so they don't get lost. So there, in a real market, this is a more serious problem. So this is actually a lot of real example of various fake part, bogus component that is deployed in military device in commercial market. Again, it's even more scary. So, okay, to prevent this problem, we proposed a solution to DoD back in 2014. We fabricated several test sheets in company, in university, also environment, and we're using to a red team, chipworks and textplane for attacking our design. So the idea, essentially, at the core of counterfeiting cloning is reverse engineering. If you can do reverse engineering, then you can have access to your entire design. You can know what your design is doing. Then you can, if you have, for instance, netlist of your design, you can see, okay, if I put a couple of transistors here in this design, it's not going to come up in the netlist, in the logical operation, but it's going to be activated only at the day that I want, and therefore you can control the design when you want. So reverse engineering is at the core of a lot of this counterfeiting or production trojan and so on and so forth. There are two companies, major companies that do reverse engineering. The process is very similar to the design. They do front end, back end, synthesis, placement, floor planning, and so on and so forth. Here is exactly opposite. And let me walk you through some of the steps very quickly. First, we need to depackage the design with some nitric acid or other material. Get to the silicon layer. Then silicon are built in 3D. At the bottom layer we have the silicon, we have the transistor, on top we have metal 1, metal 2, all the way to RDL, redistribution layer. And the attacker, now reverse engineer, need to go and remove metal one after another, keep the information for the connection, go all the way to the transistor layer, take image, and then it has the entire netlist and the entire design. How they do it? With SEM camera. Okay? With SEM camera, they zoom into the design. They take image of the design, how it look like. And this is the same camera actually they're using it for if you publish a paper in IJSCC or Solid State Journal or conference, they're using the same camera to show that their design, what interesting novelty they have, RRAM, FERAM, etc., new technology and so on and so forth. But here they're using it to find out the layout. After they remove metal layer one after another and they take image of every layer. Then these images need to be labeled. Very similar that we do labeling in front end to back end. They do reverse labeling, identify where the memory log is, where the processor is, where the input, output, where the Bluetooth is, just some high level labeling to identify the ports. And then the next step, once they identify the major components, then they do image processing. This image processing is very simple. Actually, we're able to do it also ourselves. We develop a software. This is how the layout looks like. They feed the layout to image processing software and they detect the netlist. And why they can detect it? Because the layout follows standard. The inverter is always going to be the inverter, right? The image. We have image processing software now to detect monkey, various objects. The same software, which is using convolutional neural network, this is being trained here now with a very small database. How big is our database? Maybe 100. We have 100 AND gate, NAND gate, NOR gate of different size, add process variation on top of it. Still, we're not talking about like millions or billions of images. So in fact, we're able to replicate this with a simple 3 to 7 layer, depending on how much accuracy we want to get, neural network, CNN. Very simple. And there's open software D-Gate. I think the last time we checked it, they want to start a company out of it. It's not available anymore. But D-Gate used to be as open software to do that. So this is a taxonomy of various defense and attack mechanism before I introduce our solution. The field is very crowded. Okay. On the defense side, I listed all of the defense from 2019 to 2018, highlighted also in the red, the one that we proposed. On the right side, the attack. As you can see, the almost for every 6 months, 3 to 6 months after a defense solution was proposed, someone were able to attack it and reverse engineer the design. So this is actually scary because no matter what solution you have, someone definitely in 6 months can reverse engineer it, but it's good for academic because we always have a problem here to solve. That's a good part of it. So the solution that we're proposing here is to use lookup table. And lookup table, many of you know, it's being used in FPGA, they're programmable. You can program lookup table to be whatever you want, whether it's AND gate, NAND gate, NOR gate, a combinatorial function, and so on and so forth. So in the design, the idea is to identify part of the design and replace them with lookup table. Then when you send this design with partially lookup table, partially programmable to Foundry, Foundry doesn't know what this design is going to look like. It doesn't have access to these programmable bits. Once the design is back, you can program as you wish. Okay, but I'll talk about how this is still going to be vulnerable and what kind of mechanism we can put in place. So why lookup table make the design more secure? In fact, if you have a lookup table, if you have two input lookup table, how many combinatorial logic you can maybe satisfy with that? 2 to the power 2 to the power 2, right? 2 to the power 2 would be 4, 2 to the power 4 would be about 16, right? Not about exactly 16. It's not too many, right? Attacker can try all 16 possibilities and find out and apply the input, observe the output, and see, okay, if this is an AND gate, NAND gate, NOR gate, and so on and so forth, and done, right? 16 is not big. But imagine if you have n lookup table, and n, if n is 10, how many combinatorial function you can realize with this 10 lookup table? 2 to the power 10 is centillion. Centillion is the largest name number. Essentially 1 followed by 3030. Meaning that for one of these lookup tables in the design, and you could have many of them in the design, the attacker need to try all these possibilities, then combine this with all other lookup tables, multiply them. The space is enormous. You cannot just navigate it in linear time. You have to deploy some other solutions such as SMT or SAT, SAT-based attacks, satisfiability theory, which we'll talk about. So there are several challenges. Yes.
But all of the lookup tables are relatively small.
Yes.
Because otherwise it's very inefficient.
Yes.
So why not have a structured way on the attack, the way that we're doing the design itself?
Mm-hmm.
So you don't need to have this combinatorial explosion. I mean, the lookup tables usually are 32 bits, which means 2 to the 5th.
Mm-hmm.
So if I have 2 to the 5th here, which is combined to 2 to the 5th here, I don't need to have a 2 to the 10th total combinations. I can have 2 times 2 to the 5th. Which is 2 to the 6th, and I can figure out everything.
Absolutely. That's a very good point. So initially, before 2015, where a new type of attack body was introduced in the community by Sharad Malik at Princeton, it's called SAT attack, satisfiability theory. And the idea is the same. Or how many of you work with SAT, satisfiability theory? Right. So it's if you have a combinatorial function and you want to find essentially a value for all of those parameters that makes that satisfy that combinatorial function, you don't need to explore it brute force in a brute force manner. Instead, use SAT, and SAT essentially in a random fashion, I should call it, with some seed function, you start removing keys after another, eventually narrow it down, and quickly solve the problem that what parameter would satisfy that combinatorial function. So before people brought SAT into hardware security community, that solution was the best, essentially, just to populate it. And we proposed in 2014 that. But then, after SAT treat that too many in linear space. If you have one lookup table versus 200 lookup table, the solution can be, essentially, SAT can remove all the key almost in the same amount of time. And the reason is that divides the netlist into smaller part and try to understand each of them. Same way divide and conquer sort of approach. So it really doesn't care as much as these lookup tables are not communicating directly, or even if they're communicating directly, it try to reduce the space by applying various statistical analysis technique. But eventually what the paper shows is that the number of lookup table, and I'm going also to show some of result, is not really going to make the attack time exponentially higher. It's just incrementally going to increase it, and incrementally is not really helpful for us. So, yes?
Sorry, can I ask you something?
Yes.
If I understand correctly, the contents of the lookup tables is fixed.
No, it's programmable, depending on what technology you're using. For fabrication, you're using if-use, which is you program it once. It's one-time programmable OTP. But if you're using alternative technologies such as STT, MRAM, MTJ-based, non-volatile based, which you're using in an alternative fabrication, you can program it. But you have to program it through the JTAG, through the daisy chain of the JTAG.
I understand, but so in the case it was fixed, then wouldn't I use the same procedure also to look inside what's there in order to reverse engineer it?
Absolutely, absolutely. If it's fixed, then as attacker remove metal layer, they can see the program and the bits what it looks like. There's 0 or 1, especially for if-use, right? For if-use, it's a fuse, right? You burn it, and they can, when they use SCM camera, they can see the content. It's a 0 or 1. But and that's why for security, we don't have absolute measure, essentially. We just want to make it more and more difficult or more and more expensive for the attacker. It's not like performance. it is really relative to attacker capability, right? Adding ifuse would make it a little bit more difficult, but definitely attacker, if they deploy more resources, if government is behind it, they can reverse engineering. Now we go to the next step, which I'm going to talk about. We are deploying STT-MRAM technology. STT-MRAM, I'm going to explain why it is not detectable when we remove the metal layer. And that's a very good question. So, to realize a solution, if you present this idea to industry will say that, okay, why this idea doesn't disrupt my standard design flow. First, this idea has to be manufacturable. You cannot just simply bring lookup table to your design. It's expensive, as indicated, 32 bits. 64 bits, the maximum number of lookup table input, 5, 6, 7 FPGAs are around that number. Also, the solution has to be competitive with custom ASIC. The one I show you, the ASIC design is very complex, various steps involved. You cannot suddenly introduce a big chunk new step in ASIC design. Companies are not going to adopt it. The solution has to be competitive with the custom ASIC. Also, the lookup table design has to be compatible with CMOS. You cannot introduce a technology that cannot be integrated with CMOS. And it should be secure. The programmable bit should not be accessible. You cannot just use the one I told you, OTP, and put the programmable bit on the chip because you make it accessible. Or you cannot put it in the third-party memory. Because if you put it in the third-party memory, every time the design boots up, you read the programmable bit from that third-party memory, you just push the security to something else. That third-party memory becomes the source of vulnerability. That's not a good idea. So, to address all of these challenges, again, there are so many other, but what we relied on was using fancy technology. I'm calling it fancy. That was fancy 2005, 2015, 16, and not anymore. It's now a lot of products are out there. BMW car, Mercedes car, they're using this technology in their Everest. It's a big supplier because of many reasons which we can talk about. So this is a relatively new memory technology now in commercial market. Spin transfer torque, random access, STT-MRAM. The advantage is it's non-volatile, okay, unlike SRAM. It's easy to program. They have some challenge with write-read operation, but they've been addressed. They're scalable and they're CMOS compatible. They can be integrated with CMOS. They have near zero leakage. They have reliability against process variation. Okay. The good thing also is that for MTJ, the information is programmed in form of magnetization between metal layer. In most cases, between metal 2 and metal 3. So what does it tell us? When the attacker tries to remove metal after another to go to the silicon layer and it take image of all the metal connection and also the silicon, as soon as it goes to the metal 2, remove metal 3, remove metal 3, the data is lost. And actually this is what companies are reporting to us. When they remove metal to go to the magnetization layer, metal 2, metal 3, as soon as they remove the metal layer, all of the data that we store in the lookup table is totally lost. And this is assuming that the attacker have access to post-program design. Here we are, I'm making the most difficult assumption. If attacker doesn't have to post-program design, obviously they cannot reverse engineer. But here I'm assuming that attacker now have access to the fully functional device, which is programmed. Then what they do, they take it, they remove metal after metal, they go to metal 3, they remove it, they go to metal 2, then they lose all the bits for this lookup table and gone. And it's magnetized. It's not like physically stored somewhere. So that's why this is, again, I'm not saying ultimate security because tomorrow someone could for sure is going to break it. It's just, again, make it more and more difficult. So we designed several circuits to realize this lookup table, to reduce the cost, back to the point that you mentioned. But again, I don't want to go into detail of the circuit. Layout, and how one of the test chips look like, and so on and so forth. But these lookup tables are obviously not cheap. They have significant performance, delay, area, and power overhead. So now the problem here, the interesting problem to look at is in a big netlist of a design. Netlist is a graph, right? Millions of connected node and edge. Which part to identify and to remove and put with instead a reconfigurable lookup table, eventually to make it very difficult for the attacker to understand what this graph is really doing, whether it's a crypto engine, or whether it's a processor, or whether it's an ALU, or whether it's a branch predictor, actually it says SRAM, so it's not a combinatorial. But anyway, so and given that we have all these challenges compared to standard CMOS. In terms of front end, back end, we add minor steps. In the front end, we do the synthesis as usual. Then we have an algorithm in place. Once we do the synthesis, algorithm go identify the lookup table, grab them, identify the region that we put lookup table, we make it programmable, and we put lookup table. Then we have a delay. We have additional delay for this lookup table, right? How many of you have done synthesis front end? So synthesis tools are very powerful, right? They have a lot of algorithm to do optimization to eventually reduce the delay to be able to bring up the clock frequency, right? Here we introduce some delay somewhere in the circuit, but we are not going to manually reduce this delay. We let the synthesizer tool, whatever optimization they're using, now to deal with this new additional module we put in place. So essentially, same as the standard library, we have AND, NAND, NOR, XOR, XNOR, right? We add a new module called lookup table. And the synthesizer now need to deal with this new library, which is library plus, to be able to do the optimization and meet the clock frequency. As long as we are not putting this lookup table on the timing critical path, we put it on non-critical path, we should be fine. And in most cases, timing critical path and security, they're not necessarily the same. They could be different. So, again, there are a lot of complexity here. I don't want to go into detail due to time, but we try different attack. Again, brute force, synthesization, but the most complex one is SAT, which signal skew probability and so on and so forth. I don't want to go into detail again due to the time, but again, SAT attack is something really sophisticated. It took actually us almost about a year to understand what it was. But there are three design, again, back to the, my background is architecture, okay? So every time I look at this problem, I try to understand what is the architecture trade-off here. When we wanted to put lookup table selectively in part of design, there are three questions that we wanted to answer. Insertion policy, where to insert this lookup table? Design complexity, how many lookup table is sufficient? Back to the question was asked. Should we replace the entire design with lookup table, make it like FPGA? Or maybe 1%, 2%, 3%, 5% of a design replacing lookup table would be sufficient. The third question is lookup table complexity. How many input lookup table? Should we put 2 input lookup table, 5 input lookup table, or 6 input lookup table? This is some sort of a sensitivity analysis. It's really important to do. So we try different heuristic algorithm, and this heuristic algorithm, they understand SAT attack based on how SAT attack works. We derive some heuristics, try to avoid lookup table putting back to back or putting in a primary input, primary output. We tried all of them. We published several papers on this, several other groups also published papers on this topic, and the results are very interesting. The results here show execution time on the y-axis versus the number of lookup table that we put. We call it obfuscated case. Gates that are now has been completely obfuscated. And as you can see, increasing the number of obfuscated gates from 20 for this particular design, which has 3,400 gates, we replace 20, 40, 60, 80, 100 to 200 gates with lookup table. Just incrementally makes the attack time, which is shown on the y-axis, incrementally more difficult. But if attacker takes 10 to power 1 seconds to deobfuscate the design, if you make it 200 gates, the number increased to 2 times 10 to power 1. It's still linear. Still, we really didn't make it exponentially. We want to make attack exponentially more difficult on the y-axis. So this solution, obviously, increasing the number of lookup table, SAT doesn't care, as I just said. So this is a random policy. We tried more sophisticated heuristic based. Still, not so much, not so much, not so much. Various policies that we propose, people propose before SAT attack. After SAT attack, all of them really failed. So, heuristic based method, they're not so much effective. Replacing in this big net list of a design, connected graph, which node to remove and replace the lookup table, so the entire netlist graph cannot be deobfuscated. None of them are really effective. How about the size of lookup table? This is very interesting. Actually, it's an animation. So, on the x-axis, we have the size of lookup table. On the y-axis, we have the CPU time, the attack time. The random policy, if we use 12 input lookup table, something we cannot really build it. It's so big, 12 lookup table, that we cannot even fabricate it on the block, but just simulate it. It takes essentially, the area overhead is 50x more than the area overhead of the design. 50x. It's impossible. You cannot really, no company, no agency can afford it. but it makes it definitely secure, even with SAT attack, because the number of possibility, combinatorial possibility with 12, 2 to power 12, 2 to power 2, 2 to power 12, is so many that even SAT is not able to do it, to be obfuscated. Reducing it to 5 now, with a good policy, not with random policy, would make it, now we call it SAT hard, when it is difficult to, if it's more than 5 days. 5 days is the standard. I'll tell you later why we, by community pick up 5 days for the time it takes to deobfuscate. Anything above, we call it SAT hard. And we can discuss about the detail why this is the case. But a better policy can just push this complexity down. Reliance on a very complex module, now we don't need to rely on a very complex module. We can still satisfy the design overhead with a less complex and also make it SAT hard. However, the area overhead is still 10x. 10x is not affordable for most companies, but when you talk with folks in DoD, military, they're fine with 10x because they don't have a big volume. 10x area overhead, still they can fabricate it. But still, this is not really good for mass volume. So what we can learn is that large lookup table is needed, however, it's really expensive. So instead of all this heuristic method, we developed machine learning based method to understand, to translate this circuit problem into a graph problem. And then adopt, I have colleagues that are helping, are on our team, that are in machine learning community, that are in the statistics community. They have very similar problem, but in different domain, different application. In a social media, connected nodes, connected graph. Which friends is more important? If you remove it, suddenly all of this feed, news, etc. are going to go down in the next 2 months. It's important, right, to predict it. Some similarity here, right? Here we are trying to identify which nodes are critical for deobfuscation and for obfuscation also. So what we do, we need to convert a graph or a netlist into CNF or conjunctive norm format. And then on this we run SAT. Normally that's what we do. We run SAT, and then if the design can be obfuscated within 5 days, we call it SAT soft. About 5 days, we call it SAT. Okay. Instead of using heuristic-based method to do it, what we do, we are essentially extracting various features from this circuit, such as number of gates, complexity of gates, fan in, fan out, number of primary input, primary output for the particular circuit. Also the location of the lookup table, where we insert that. And then with that, we are feeding it into a neural network. We want to find out, estimate the SAT execution time without really running it through the SAT. If we are able to do this, the lower path, then we have an instantaneous model for the SAT. We don't need to wait for SAT attack 1 day, 2 day, 4 day, 5 days. With an instantaneous model, once we extract this feature from the circuit, we know whether this solution is SAT hard or not SAT hard. Once we have this model, then we can try every possible scenario in a brute force manner. Put lookup table here, put lookup table there. Because we can see the result instantaneous. We have a model. We don't need for every model to try and wait few days to see whether it's SAT hard or SAT soft. Does it make sense? So the challenge is to develop this model. What we did initially, we spent about 6 months collecting all of these features from the circuit manually, such as the one that I explained there, to be able to see if we can establish a connection between the execution time that it takes for that solution on a SAT attack and these features. Our effort was essentially futile. No really good result. We couldn't really predict it accurately. 200% inaccuracy, 500% inaccuracy. Very corner cases, yes, we get some accuracy. But manually extracting feature, and by the way, this is very same solution that normally we do for machine learning. We extract feature, we feed it to neural network, and then we develop a model, neural network-based model. So instead, we brought a concept from very, very new concept from machine learning community called graph convolutional neural network. So essentially, what does it do? It tries to feed a graph, treat it as an image to a neural network to be able to extract feature automatically instead of manually. Manually, it was fan in, fan out, number of primary input, type of gate, AND gate, NAND gate, NOR gate, topology of the circuit. But this solution is agnostic. It doesn't know this is a circuit or whatever it is, a graph, right? It automatically extracts feature very similar to image processing. How do we do image processing using convolutional neural network? How do we do it? We have an image, right? we feed that image to a neural network. Neural networks, through various layers of the neural network, from the first to the max layer, it extracts features, and these features are meaningless. In most cases are meaningless, right? The challenge is, image is 2D. Graph could be n-dimensional, right? But the community, machine learning community, were able to figure out how a graph can be converted into a bipartite graph, and the bipartite graph then can be nicely translated into an image-like, and the image can feed to a neural network. Then all of the features we extract from the circuit are totally meaningless. We don't know what these features are. The features could be 2 times number of input times number of flip-flops power to -5. But who cares? As long as it works, it works. That's the beauty of neural network, or maybe the ugly part of the neural network. But did the model that we developed, the 6 months manual effort, no success. 1 month, 1.5 months of this effort, absolute success. So this is actually also a paper we recently published on the day. No, actually, sorry. Published this in this year, Chess or Raid, maybe. Yeah, one of them. So anyway, now look at all of these heuristic methods. They make it incremental. This new method, we call it cognitive obfuscation. It's cognitive, but we can't really understand it. We cannot interpret it, but it's working. And look at the result. It makes it sat hard at 80 or 100 number of inputs and done. So the next step that my colleague trying to do is try to interpret this feature. How can we, if we can understand this feature, then we can design better circuit in the first place, even without applying lookup table-based obfuscation. If we have a circuit topology of X, how we can convert circuit topology of X to circuit topology of Y without affecting the timing, power, area. However, the circuit topology of Y cannot be deobfuscated as easy as circuit topology of X. So forget about this lookup table. Forget about all of our solution. Just circuit transformation. That's actually the next solution that we are trying to explore. Okay, very quickly, do I have 5 to 10 minutes?
Yeah.
Okay, perfect. In 5-10 minutes, I'm going to wrap up. I'm going to go through the second part of the research on using machine learning for hard performance counter. I'm sure most of you on this topic, on computer architecture, they know very well. So I don't need to spend time on the maybe background. So malware, big problem. The number of malware increased exponentially, significantly. 2017, McAfee report 140 million new malware. Okay. Which is big. Just to put in perspective, this is 20 times more than the number of apps we have in App Store and Google together. So we create more malware than the number of benign programs, which is the problem. So the traditional solution the software community came up with, or not software, again, I don't want to tell me. The traditional solution that we have is using antivirus. Okay, they're great, they're working very well, but they're expensive. They're also vendor database dependent. And these are solutions that, for obvious reasons, we cannot really expect to deploy them in IoT devices, right? Because we can't really, first of all, we don't have enough space in IoT devices, 4 kilobyte, 8 kilobyte of the memory to have a signature database, and etc. Or a lot of these databases, they need to be updated. In IoT devices, communication is very precious. We cannot keep sending, updating the signature on a daily basis. That's definitely not going to be a solution for IoT. So the solution that was promoted in 2013, ECE was to use this performance counter, okay, to extract feature, and from this feature, hopefully we can detect anomaly compared to normal program, okay. 2013 ECE, the group at Columbia, they observed that if they look at branch predictor, they look at some other traces, HPC traces, and they observe that the traces for malware and the traces for normal program, they're slightly different. If we can combine these together, maybe we can detect anomaly. Great. So they proposed several solutions for that. However, they, oh, by the way, so what is hardware performance? Do you know hardware performance counter? What it does? Or so let me very quickly just summarize what hardware performance counter they do. These are registers, dedicated registers that manufacturer like Intel or IBM or ARM, they put in processor mostly for performance tuning, to collect data in real time from running application, to provide feedback to the end user that your application that you're running may be suffering from cache misses, may be suffering from branch misprediction, maybe optimize your application. Okay. However, if you look at most today's architecture, we don't have many of them. We have maybe 5, 6, 7, actually 6 in many cases. And one reason is, we talked with folks at Intel, one reason is for obvious reason, they don't want to disclose or give end user the entire view of their architecture. They have the very limited of them. They're expensive. Actually, there was maybe a paper about mentioning by a group actually in Sweden, I forgot them, that they're expensive. They're really not really expensive from physical implementation. They're just a register that collect data sitting on, in most cases, not critical path. Even if they sit on critical paths, between the ALU and that feedback loop or bypass logic, still you can manage it. Just register, just monitor. It's not really holding data. It's not really sitting on the exact critical path. So they are not really expensive. They're a bunch of registers. They collect information. These manufacturers, they don't want to disclose the entire architecture to the end user. For obvious reasons, we have limited of these registers. However, we have thousands of events that are happening in the processor from front end to back end. And we should be really careful, and we should really on how we are using these very limited resources in real time to collect traces. 4 out of thousands, or 4 out of 100, some number about that. So again, we use them for various performance prediction, for power prediction. Now we are trying to use them for security inference. Whether from these traces we can infer security violation, depending on application, what is running and what. So several papers published. I started from ISCO 2013 and highlighted also our recent work. We have almost every year in DAC, 17, 18, 19, date 19, also ICCAT 2019. Papers on this topic, hardware-assisted malware detection. We are not also focusing on malware. We're looking at various other types of attack. So let me go through very quickly the challenges with detecting malware using machine learning assisted hardware performance counter. There are 3 challenges that are highlighted. The first one is the number of performance counter. They're limited. We have hundreds of events that are happening, and these events are traces from running application. Which one out of these 100 should we collect for the running application to be able to look at only these few to detect malware? That's first a big question, right? And in fact, we did some analysis. We use several machine learning algorithms from Bayesian net, SM or Red3, 1R. 1R is simple rule-based. The different machine learning algorithm belonging to different class of machine learning domain. And here we tried with assuming we have 4 hardware performance counter versus 8 versus 16. As you can see, in most machine learning algorithms that we tried, the accuracy of the classifier between malware and benign program is heavily dependent on the number of HPC that we can collect, or number of data we collect. The more, the better. But to some level, obviously. At 16, you make it 32, you see some maybe saturation, or maybe it's not the result of not going to converge. But this is definitely important. The second challenge is which out of these so many events you should look at. So in this case, we look at backdoor, trojan, virus, rootkit, worm. We have a large database. We work with companies to get some of this data, also several of them are also available online. And the results were very interesting. For all of this class, the first 4 events that are happening in processor are the same out of all these 100 plus events. The first 4 are branch, cache, branch miss, and also node store. These 4 are the same. The rest are slightly different. So no matter what class of attack we have, the first 4 events out of these 100 events that are most dominant in various machine learning classifier, we found it to be the same. And this is intuitive because if you look at these 4 events, they are mostly related to control flow and data flow. And what attacker they do, the attacker normally they want to redirect your control flow or data flow, right? To somewhere in the memory that they have the attack code that destroy your hardware or destroy your software or whatever. So that's why it makes a lot of sense why these first 4 are the same for all kind of attack. The remaining are not so much. That's why we need to customize solution depending on the domain we're dealing with. The third challenge is the machine learning classifier, which algorithm we use, whether we use neural network, whether we multi-layer perceptron, whether we use simple 1R, whether we use Bayesian net. The depending on the assumption, depending on architecture, whether architecture have 4 HPC or 8 HPC or 16 HPC, and depending on the domain, whether the application is Trojan, virus, the winner of machine learning classifier is different. So we can't just deploy a Bayesian net algorithm there and hope that any future type of attack can be detected highly accurately. No, the winner sometimes could be J48, very simple rule-based algorithm. The winner could be NLP, multi-layer perceptron. So that calls for maybe a reconfig or maybe programmable machine learning algorithm. So these are 3 challenges that we identify in recent work. These are some of the, again, infrastructure. We're running it on real architecture, on platform. We have Linux container. We are using Backup for machine learning classifier. We have more than 5,000 Linux executable, malware, and etc. Actually, that number is much higher than one that we're using right now. So here we are using, I have, I think, 10 more slides very quickly to wrap it up. We have, we're using PCA, principal component analysis, to first reduce the number of events to address the first challenge. We have 100. With PCA, we are reducing that 100 to something 16. Still 16 is way more than the number of hardware performance counter we can afford. So for the second solution that we have, we are using ensemble learning. We know that the winner of classifier is not, could be some, any one of the machine learning classifier that we studied. Also, how can we detect, how can we rely on fewer feature? 16 is what we want, but on real-time platform, we only can read 4 at a time, right? Unless we run malware multiple times, or application multiple times, which doesn't make sense to collect 16 because we need to run it 4 times. So instead, in this case, we are using ensemble learning and AdaBoost. What AdaBoost and ensemble learning they do, they combine weak classifier. How they combine it? There are different algorithms to do that. We can do pooling, we can do feed forwarding, we can use the output of one for the input of another, various solution. You have to try and see which one works magically. I'm serious about that part, magically. So that's actually the part about machine learning. So ensemble learning essentially combines some weak classifier, in which case we have weak classifier out of 4 HPC. We want to get the performance of a 16 HPC, and assuming that we had, what if we had 16 performance counter in place? This is a solution that I'm going to show the result how it looks like. And the third solution is, we don't know really which machine learning solution we deploy, whether Bayesian net or so on and so forth, right? So the solution here we proposed in day 2019 was to use a 2-step prediction. The first step prediction, first we identify with some level of accuracy what application we are dealing with. Whether the application is Trojan, backdoor, rootkit. Remember, for each of them we had a different winner. And the second step is, once we, with some confidence, we identify what application we are dealing with, then we are calling the right classifier to deal with that application classification. So this is what we call a 2-stage malware detection. So the first step, with some confidence, we identify whether we are benign or one of the 4. And the second step, we are deploying whatever we are proposing. Actually, the base is going to be that winner. On top of that, we add AdaBoost and ensemble learning, which I just described in the previous slide. The result is very interesting. Here are the results. We can increase the accuracy from 80% all the way to 98.1%, which is great. 98.1%. This means that we have a solution that can detect malware with such a high accuracy. This is a multi-billion-dollar solution, right? But is this all the, maybe everything I described is, does it look so rosy as it is? Any maybe bug in whatever I just described? Any problem?
This is for known attacks, right?
Actually, this is for known attack, you're right. But we divide the database into 70%, 10%, 20% for validation, for training, validation, and testing. So with testing, we are putting that, but you're right. This is all what we have seen, but our classifier really haven't seen that 20%. Any problem you notice here? If I have a 98% accuracy, I could definitely go make billions of dollars, sell it to companies, but it is not really that easy. The problem that we had in all of our published paper, including paper published in architecture community, ECE, HPC, etc., is everyone make a big assumption that malware spawns as a separate threat Meaning that the data that you read and you test you train your neural network or classifier or whatever, is a clean data belong to malware or clean data belong to normal program, right? What if malware embeds in normal program? Here actually we did a very interesting test. There is again, big data community always come up with interesting visualization solution. They have now a new method. Actually, it's a paper, thousands of citations, very recent, 2017. T-distributed stochastic neighboring embedding visualization. If you have a high dimensional data, you can visualize it with this method to see if you can see a trend. Before even trying machine learning method. The one on the left, here we show the benign and malware program using this method. And what is explained for this data set with a high dimensionality of 100 plus features, machine learning can be effective. You see, the malware and benign can be distinguished with the naked eye. That means that you can deploy a machine learning algorithm to be effective in distinguishing the two. The one on the right is we run a test, and in this case, we embed malware in a random, fire malware in a random time inside normal program, and they collect the data sample interval. Can you distinguish malware and benign here? There is no cluster. This means that machine learning algorithm is not going to be successful here. Even don't try it. This method is essentially a pre-process of whether a machine learning algorithm can be successful. If malware and benign program are embedded, this is the real result. Here, we ran 10,000 test case, and we fire malware at a random time in between a thread that normal program was able to run, was running. And look at the accuracy. The accuracy is not 98%. The accuracy is 30% to 70%. Because the data that we collect to train is already polluted data. We do it intervally, right? Intervally, maybe the first 1 millisecond could be malware, the next 10 millisecond normal program. We don't know when the data that you're doing the training testing, where it comes from. So detecting embedded malware, which are obviously standard malware, are very difficult. Okay, so this is the last part, and I guess that's it. We have also some other effort ongoing. We developed a new attack, SAT attack. We are also, actually, one slide here I have, we call it adversarial camouflaging. How many of you have heard of adversarial machine learning? When you have so adversarial machine learning, the concept is very simple. Image processing, right? For image processing, we feed the neural network with maybe thousands of images. And then we hope that, okay, the next image, the neural network should be able to understand what this image does. And that's how smart car they do. 2015, Jan Goodfellow from Google, he demonstrated that on a stop sign, if you put a couple of maybe pixel, a couple of stick, put it on various parts of that speed sign, the neural network classifier of several machines, automotive, so several cars, that were trained aggressively, they mistakenly identify that speed sign as a stop sign, or maybe vice versa. Sorry, stop sign as a speed sign. So the automotive system essentially failed completely. We're just sticking a bunch of several pixels in that stop sign image. So that way we can mislead machine learning classifier to classify an object as something else than what it is. So we deploy the same concept, we brought it now to layout. Remember, for image reverse engineering, the attacker have to run image processing software to detect whether it's AND gate, NAND gate. What if we pollute the layout with a bunch of sticker now, but our sticker now are metal fillers. Metal filler, we have to use metal filler for fabrication. We just need to put it carefully in the layout to mislead the image processing software to classify an inverter instead to be an AND gate or NAND gate or NOR gate. This is what a new concept we introduced. We haven't published any paper on this. We're still working. We call it adversarial camouflage. Same concept, but in hardware security community for reverse engineering. And I guess that brings it in. Thank you.
Maybe a couple of questions from the audience?
Yes.
I have one. Actually, I want to talk about the malware case. Which is the case that malware is actually in a separate thread? In which cases, what is the frequency ratio between the form and the latter?
Actually, I don't know. I don't know that. But I would say normally when we train most sophisticated attacks are embedded malware. Okay, we should design our system for worst case scenario, right? Embedded. If it's not embedded, I'm sure simple algorithm like what we presented. There are other groups that they demonstrated can take care of it. But the most challenging one, the most sophisticated one, are the embedded one, and we should design a system for those. The frequency, I'm not sure.
Any other question? Okay, let's thank Houman again.
Thank you.